Hello everyone, in this video I'm going to be continuing our introduction on momentum. So before watching this video, hopefully you were able to see this video of a golf ball driving, hitting a golf ball. And you'll remember yesterday I said that really the most interesting things about momentum is when objects change their momentum. And so in this case, it's literally just within milliseconds of the driver being in contact with that golf ball. You actually saw that the golf ball compressed. In that small instance, that's where the object is actually changing its momentum. All right. Now, I wanted to show one other example of an object being hit where we could kind of see what's happening in that split second. So I'm going to fast forward a little bit. And I think that this is muted for you guys. My video recorder, I don't think, records computer audio. But you can see that when a bat is hitting a baseball, just like the golf ball, it compresses a ton. And this isn't just like a Nerf baseball. This is a Major League Baseball. Whenever it's hit, this is what's actually happening to it. This is while it's changing its momentum. So this idea of that time of impact is going to be important for us continuing momentum today. So make sure your attention is on the target sheet that you guys were working on yesterday. Notice that I still have the stuff that we ended with, our equation up here and our solved equation up here, and then our equation for finding the change of momentum. It's really just change momentum is equal to our mass times the change in velocity. But there's actually another equation for change momentum too. All right? And so change momentum, delta P, all right, is going to be equal to, and we could kind of think of what are some things that could change the momentum of an object. All right? You can imagine, for instance, our hockey puck example. Well, what's causing the object to change its momentum is a force, right? And another thing that we could do to increase that change of momentum, or that would be a factor in that, is also the time. Now, this time is not the time that the object's in the air after it's hit. It is the time of impact. So usually this is literally just a very small amount of time, like milliseconds. So think about while that golf ball is compressing, or while that baseball is compressing, that's the time of impact. Once the ball lets go of the driver or lets go of the bat, that time is no longer at play. The object's not changing the momentum anymore because of the bat. All right, so if I were to put this equation in word, change momentum is equal to my force times time. That's it. And my units are going to be Newton seconds for change of momentum. So that's actually a little bit different than the units over here. Is that okay? Yes. So there's actually two different units for momentum. You could use either one anytime and they would still work. Now, the reason why our units are Newton seconds is, remember, units have to be balanced on both sides of the equation. So our unit for force is newtons, our unit for time is seconds, so our change of momentum is Newton seconds. All right. So I like to use this box, all right, to kind of bring together all of our equations. So instead of like having like this equation and this equation and this equation, all right, really when we're talking about change of momentum, so many things are equal to each other. So for instance, I have my change of momentum, and that's equal to mass times change in velocity, right? But then we know that change in momentum is also equal to F times T, force times time. And so we could also set an equation that says that, hey, mass times change in velocity equals Ft. So it just depends on your situation. Sometimes your equation is going to be this right here. Other times it's going to be delta P times Ft. Other times it's going to be all our four variables together without delta P in it. It just depends on the scenario. So let's look at an example of how you'd solve this. What is the change in momentum of the hockey puck above here, all right, on our target sheet? And we actually calculated that yesterday, right, using mass times change in velocity. And we got that to be 2.5 kilogram meters per second, positive because it's going to the right. All right, now this problem is asking if the time of contact is just 0.0003 seconds, what's the force the hockey stick exerts on the puck? So I'm going to use my equation up here, the new one we have, delta P is equal to Ft. And I know that I'm solving for my force. I know my change of momentum from over here. And then my time is 0.003 seconds. So when I solve for this, I get a really big force of positive 8,333.33 newtons. And again, positive means it's going to the right. All right, so that's just an example of how we would solve word problems there. Now, today we're going to be working or refreshing ourselves on proportional reasoning. But the big thing with today that's new is that multiple variables are changing. The nice thing is there's really nothing new to this. It's really just doing the exact same thing we've done before, just multiple variables happen to be changing. So let's look at this example. Two golfers are practicing their line drives. Vandy hits a ball with a force of some force with some time, and it leaves the tree at 175 miles per hour. So I have a unit right here, and so I know that that's an actual number on my table. All right. And then it tells me that Colin hits the ball with, it has the same mass, same golf ball, but he hits it with twice the force and in a little bit less of time, 4/5 the time. So the question's asking is, by what factor is the speed of Colin's ball different? And then lastly, I want to figure out what that actual speed is. So I know that the factor I'm going to look for is something to do with velocity. First, I'm just going to write down what factors do I know. I know my force is twice as much. I know that my time is 4/5 as much. My mass is the same, so that means it's 1. It doesn't change. And then my change in velocity, all right, is going to be what I'm looking for. And you might be wondering, well, Mr. Wolfe, wasn't the final velocity 175 miles per hour? Why are we looking for change in velocity? Well, the initial velocity was 0. So whatever the final velocity, that's going to be your change in velocity. Now, another thing you might be wondering is, well, Mr. Wolfe, how did you know to think about these variables? So that's when we're going to be looking at our equations. And when it comes to proportional reasoning, all right, you're going to be using these equations right here. All right. In this case, notice that we did is we just took this right side, mass times change in velocity, which is force times time. And I'm like, all right, so I have this variable, I have this variable, I have mass. I'm just looking for my delta velocity or my change in velocity. And so I use that as my template to figure out what variables I needed. So here's my equation. And my force, again, is twice as much. Time is 4/5 as much. My mass stays the same. Here's my delta V, and I'm going to just solve for delta V, which is really just 2 times 4/5. 2 times 4 is 8. 2 times, well, then 1 times 5 underneath is just 5, so it's 8/5 as much. So it's like saying 1.6 times as much in terms of how fast that velocity is going. So now I just need to apply it. How fast is Colin's ball actually moving if Vandy originally hit it at 175 miles per hour? So all I do is, just like before, I take my factor and I multiply it by the original number, in this case 175 miles per hour, and I get my new number to be 280 miles per hour. So with all these variables changing, Colin hits his ball with 280 miles per hour. So hopefully this example helps in terms of solving proportional reasoning problems. And if you need help with number 2, I'll also have a video